Hello, ladies and gentlemen. Welcome to the first lecture on mechanics of material. My name is Chiravachradej. Today I will introduce you to the subject of mechanics of material, aka strength. Okay? We will go through certain topics before we can see the overview of the subject mechanics of material. First, we're talking about how we actually categorize our work in civil engineering. That will guide us to what we actually have to do with the task, which will be more related to the subject itself. Once we realize what we have to do or what does it involve with our work, then we will go into more details and in fact just the overview of this subject, mechanics of materials. We could categorize the structure or our work into its function. Maybe we could talk about accommodation, housing. Okay? We could talk about maybe some kind of transportation structure. This one is just roads. Or we could talk about the mass transportation system. We could talk maybe about bridges, of course, to go over water or between cliffs. Or maybe even up to the dams. These are all our work. Well, as I always emphasize, our work makes civilization possible, but that is not really the point of today. How about we categorize it in some other way? Sometimes we look at it as materials. What material do we use? Bring back the housing, right? This one here, we actually use structure material. We use the reinforced concrete plus some stoneworks, mason works. Some other structure might be more dominated by steel structure. Like this one is the bridges. Some bridges, these are kind of like the truss. How about what we have to do with it? No matter what you categorize, no matter how you call it, house, roads, bridges, or even reinforced concrete, steel structure, what do we have to do as a civil engineer? As we all know, the main task, the first task we know about civil engineer or any engineers is to guarantee the safety of the public. This idea of safety will be related to the word strength in general, the strength of material, how much material can withstand the force, and how do they withstand the force. One thing that might not be so well known or widely known as much as strength or safety is about confidence, meaning whatever we do, we have to ensure the public that it is not only it doesn't fall, they have to believe it, that it doesn't fall. They have to be confident that the houses, the bridges, and all the transportation system doesn't fall down. Not only they have to be safe, they have to believe that they are safe also. And that what we actually ensure is what we call small displacement, meaning there will be very little deformation in our structure. The building you see actually deform under loading. However, it's so small, it's so slightly, you can never notice it. And that is what we have to assure. And this is more related to the subject of this course, the mechanics of material. As I said, aka strength of material. It's the nickname we used to call it is strength, and I think you guys still call it strength this day. Okay? So, now, what do we need to know before we can ensure the public safety? What do we have to know before we can ensure the public confidence? A house needs a foundation. Our calculation, our learning also need a foundation. We have to understand the external forces system. Basically, there are some applied forces into our structure. We have to understand that how would the structure react, how would the support react to become the total system of external forces, applied forces and reaction from supports. And that is in our statics. We also have to understand that, and we have to be able to calculate that, how this system of external forces affect the system of internal forces. We have done a lot of work in our static, in internal forces. In fact, last semester we spent half a semester looking at these forces. Before we go on and use this foundation to calculate whatever we need for this course, maybe it's time for us to discuss about what they are again. Just remind us what they are. In general, in your study, we tend to talk about the two-dimensional world. Even though we are in three-dimensional world, don't lose sight of it. The only reason that you actually study two-dimensional world, it is because it's easier to understand. But it is not the real world. You have to have the picture of the real world, the three-dimensional world all the time. Yet, having said that, started off with, we talk about the 2D world first. When we calculate two-dimensional problem, internal forces, we have one axis of axial force, one axis of shear force, and one axis of bending moment. We'll look at the physical side of it after we discuss on the topic first. Okay? Then, if we expand the idea into the 3D world, okay? Form the two axes of forces, one axis of moment, the third axis usually, as I usually call it. Then we having full operational three-dimensional world, meaning three axes of force, x, y, z. We have three axes of moments, x, about y, and about z as well. Therefore, there are 6 of them. In these 6, one will be axis of axial force. We also have 2 axes of shear forces. We also have 2 axes of bending moments, and we have 1 axis of torsion. We will look at the physical of it before we move on to the next topic. Let's discuss about the 2D, two-dimensional internal forces first. Okay? Think about this one as x and y according to the material. Meaning, if I turn the material this way, the alignment this way, meaning you should think about this is x, this is y, and this is z. Notice this dot there. If the material is continuous, I cannot pull it apart from each other. Okay? Thinking in terms of cross-section area, meaning if you look this side here on the cross-section area, I cannot put the cross-section area here away from each other. It is attached. Whereas if the material is not continuous, just touching the two cross-section area here, which was represented by that dot before, if I try to pull it apart, now it can't go simply that way. Okay? Notice that the movement of the cross-section area is 90 degrees to the cross-section area itself. This is cross-section area. The movement is 90 degrees to it. Or sometimes we talk about the same alignment as the material. If I can pull this one, and I cannot pull this one apart, it means that when you have one piece of material, the two sides pulling each other to be attached, meaning there must be a force inside the material that resists the tension force I am applying. That one there we call axial force. Okay? If it's in the same alignment with the material or 90 degrees to the cross-section area. Again, this is not cross-section. It has to be cut and then look to the side view. Then that is cross-section area. So that is one axis of axial, as I said. The second one is about shear force. Think about it as the attempt to slide the cross section this way. One go up, one go down, or the other way around, one go down and one go up. Notice this time the force doesn't pull the cross section area away from each other 90 degrees anymore. It's sliding, meaning the movement and the force is parallel to the cross section. That is what we call shear. And again, there is only one axis of it. Okay, the last one, which is the bending moment. Okay, notice the same point there. If I apply two moments on other side opposite each other, it will start to have an angle happening. You see that one, or the other way around is go that way. Okay, therefore this one here is called the bending moment. If it's the same scenario, the dot here, I cannot make the angle at the dot. Okay, that meaning inside the material there must be moment resisting it. The reason we call it bending moment is more clear if we look at the rubber. If I apply the moment opposite direction like that, notice from the straight line it becomes curvature, this curve. This curve here is called bending, and therefore this moment relating to bending is called bending moment. Three of them. If we change the scenario into three-dimensional world, then the old one still apply. The axial force only have one axis because there is only one 90 degree to the cross section, meaning it's only that one. However, if we talk about parallel to the surface, parallel to the cross section, we have that one up and down. We also have front and back, that one. So still one directional, one axis of axial force, but two shear. This is one axis of shear, second axis of shear. Okay, moment is the same. Two axis of bending moment, because you can bend it this way. This is about Z axis. You can also bend it this way about Y axis there. Right? So as we discussed, one axis of axial force, two axis of shear force, two axis of bending moment. The other moment is about x-axis. It is not bending moment because it doesn't bend. It's twisting. Okay? This mechanic here is called torsion. Okay? So one axis of torsion. All combined, 3D world, three axis of force, three axis of moments, so 6 of them. Imagine this. Well, the word axial, as I indicate, it should be relating to axial forces, right? So let's imagine the simplest application. Just a piece of material. Could be rubber, could be a ruler, it could be any piece of material. Okay, and then you pull it apart like that. In this way, well, if you look at the picture, you should realize that it's guaranteed that it's only axial. There will be so little. If the material is light enough, meaning we can ignore the self-weight, then there will be no shear, there will be no bending moment. It's just pure axial force. Okay? This is in three-dimensional picture. That if we look at the front view here, let's say original length is L. Okay? Before you pull it's L. Now, once you pull it, notice the word pulling it. The word pull it means the material will be in tension, correct? If it is in tension, then you can imagine once it's subjected to the force, it must become longer, meaning there will be some change in the length in a way that it becomes longer. Let's define it. Delta is the measurement of the change in length, not the new length. Just the change in length, meaning the new length will be original length plus the change. In another word, L plus delta, it will become a new length. A new length. The original length L, the change delta. Okay. Now, as I emphasized so many times, and I will say it again, delta will be directly related. The formation will be directly related to internal force, not external force. So, to look at the internal force, maybe as usual, we look at the sub-free body diagram, cut through the material, well, imaginarily cut it, and then see what happened, draw a new free body diagram. Okay? Originally, on the left hand side will be just the load P as before. Then we have zero shear, we have zero bending moment. In this case, we discussed that already. Then we have the unknown axial force N. With the equilibrium, then N must equal to the load P. Okay, and of course the tension. Now, what we will do next will involve the cross-section area. Therefore, let's define it first. Just emphasize it again, shall we? Look at the 3D picture, the one on the top left. The cross-section area is not the front view area. It must be cut and turned. That dotted line there. That is the cross-section area inside the material. Meaning, from the front view, if you want to see it, you have to cut through the line 1, 1, and then turn 90 degrees to see it. The side view, basically. If we draw it, it will be different dimension from what we see in the front view. So let's not get confused which area it is. It has to be that A has to be cross-section area. In this case, 1, 1. In other cases, it depends on what and where you cut. Okay? Now, we know when we pull it apart, it becomes longer. The question is, so what? It doesn't help any calculation yet, right? We need certain relationship between N and delta, and then we can use it because we can find relationship between N and P. And then if we know N and delta, we can also link P to delta. Okay, so that's the idea. Now, how should we do it? In this sense, it's not something you can just calculate. To get this relationship, apparently it has to be experimental, right? So basically, you bring a piece of material and then you pull it. You measure the force you pull it, which relating to N, right? And then you measure the displacement that happened. Maybe you pull it lightly, and then you measure delta. You pull it harder, and then you measure delta again, and then you plot the graph between N and delta. Okay? Apparently they did it, sorry. And they get, well, if they don't pull it so much, they pull it lightly, release, pull it lightly, release, but harder and harder, right? Apparently they have a straight line. Better still, it's not only straight line, it's go up and down. Meaning you pull it, it becomes longer, you release it, it shrinks back to the same shape. And everything is in linear line, which is nice because this relationship is a linear function, meaning the way you calculate it is quite simple, right? Now, they realize something though. The concept is nice. However, they realize if the material become bigger, cross-section area become bigger, what happened? Apparently, it seems like you need to pull it harder to get the same delta, isn't it? So, this graph then might not be as usable as we think. So, what they do is they experiment it as well. There's no guesswork here. This is all experiment. So, they cast using the same material. I have to emphasize, using the same material, they cast it bigger. They use a bigger cross-section area and smaller cross-section area, okay, and plot them alongside. As you can guess, your feeling is not so much wrong. Apparently, if you increase the size of the cross-section area, it becomes fatter. Right? Apparently, you need more force. Right? If you draw a vertical line cutting through all three lines here, right? You will realize the bigger, which means the same delta, the bigger cross section represented by the blue line, you need more force to get the same delta, whereas the green line, which is in fact represent the smaller cross section area, you need less force, right? So apparently they think, well, this is not so usable then. It's not so useful. Why? Because our structure doesn't have always the same area. One column to another has different cross-section area. So if we leave it this way, meaning every time we have a new cross-section area, then we have to test it again. Or otherwise, we have to use one cross-section area all over the world. There's no bigger, smaller columns. Must be one column, one side of column, which of course you should realize is not really useful. So they have to think about this idea again, about this graph again. So they said, well, since the bigger area need bigger force, maybe we can neutralize by dividing them. Okay, so maybe we change the idea of the graph. Rather than plotting axial force against displacement, can we plot axial force divided by cross-section area against displacement then? Well, asking doesn't help, trying does. So that's what they did. On one axis, now the vertical axis is no longer n, is n divided by area, axial force divided by area. The horizontal axis is still displacement, the change in the length, right? Now they plotted. Apparently that three line of graph we saw earlier become one line. Well, close enough. Any cross-section area will have the same line. Meaning it's not only bigger size and smaller size, it means that you could be in any shape. Circular, rectangles, square, hollow tube, I section, whatever. What matter is the area of the cross-section area. Okay? So since this one is so useful, so n divided by the axial force divided by the cross-section area, therefore is kept and defined by the word axial stress. The symbol we use is sigma to define the stress, which is S, lowercase s in Greek. Okay? And that stress, axial stress, is equal to the axial force divided by the area. The unit is obvious, force per unit area, and in fact we have stated that before. Seems like everything is perfect. Seems like everything is peachy, right? If you want to know the displacement, you calculate n, the axial force, then you divide it by the structure cross-section area, then you can work out what delta is from the graph, or maybe some kind of straight line function. Simple enough. But however, they realize something. Maybe it is not complete consideration yet. They think, if I change the dimension of the cross-section area, that is 2 axes, right? An area lie in 2 axes. What about if I change the other dimension of the axis we haven't actually tried? In this case, meaning the length. What happened to it? So again, they make the material with the same material, but the different length. Okay, don't forget cross-section area doesn't affect anymore because we can neutralize it already. So now what they try is varying the length. And what happened is here, like that. The longer it is, the longer the original length is, the delta, the displacement become larger. Right? Think about this. If you draw a horizontal line, meaning the same level of stress, the same level of n divided by a, the same level of stress, right? The blue line, which is the shorter one, has a small displacement. The red, which is in the middle, have the medium size displacement. And the green, which is the longest in this graph, is in fact having larger delta displacement. Again, this is not really applicable, not really useful in terms of calculation. Again, the same reason. We do not and we cannot say that. We are not building any member unless it has this length only. It's just not very useful idea, is it? So the idea then, we have to neutralize the length too. And now, the same idea, the longer the length, the longer the displacement. Maybe we can neutralize it by dividing them again, right? So, change a little bit of the idea. Now, it becomes on vertical axis, the stress, horizontal axis, we use displacement divided by original length. And here it is, the graph. There we are. At any cross section, any type, anything, right? And any length at all, you will end up the same graph as long as you do not change the material. Well, similar enough, very, very close. Okay. So again, let's define that displacement divided by original length. They call it axial strain. Apparently, there are so many ways to measure axial strain. In this course and in our work as a civil engineer, they will be about the same because we are talking about small displacement all the time. Okay, so we will relate to the one that's simplest to calculate, which is the engineering axial strain, calculated by the displacement divided by the original length. The symbol we use for it is epsilon, lowercase e of Greek letter. And this one, if you notice the unit, displacement, the change in length is still the unit of length. Centimeters, millimeter, meters, right? Original length is also unit of length. Therefore, divide the two together, the unit become 1, or what we call dimensionless. So, in this case, what happened is this. The idea is this. From the external force, then we should be able to calculate internal force. This is static, correct? In this case, let's focus on axial force. From external forces, then you can calculate axial force of any member in the structure. Then you can calculate stress because you know, or in fact we will be told, or sometimes we indicate ourselves what is the cross-section area. Then the stress can be calculated by axial force divided by the area. With the graph or the straight line function, we can relate that stress into strain. Once we get the strain, because we know the original length, we can then predict what is the displacement. Or in fact, the word predict sounds a little bit guessing. What I meant is calculating what is displacement. So far so good. One problem. This is not the complete picture of this axial stress strain diagram. This is just a beginning part of it. Because as I said, we do not pull it so largely. We pull it a little, release, pull it a little more, release, pull it a little more, release. If we keep pulling it until it fails, the graph will be slightly bigger. Well, slightly, I think probably a lot bigger. This is the graph, the total graph. Okay. The first section of this graph is the one that we just discussed, the one that is a straight line function, right? There, this one here. It is called elastic region. Why does it call elastic? Well, because the material behaves as if it is an elastic band. You pull it, it's extended, it's become longer. Release it, it goes back to the same shape, exactly like elastic band. Okay. In fact, if you change the stress, become compression, it's still the same idea. You compress it, it becomes shorter. You release it, it goes back to the same original length. Okay. Now, the second part, after you pull it up to a certain point, you will hit the plateau, the horizontal line there. That line meaning you do not have to add the force. The displacement keep increasing, right? That one there is as if the material give up. So that zone is called yielding. The word yielding means giving up. Okay, so basically it means material doesn't resist the force anymore. The same amount of force, displacement keep going. And then the third region, it is starting to be able to resist more force again. That one is called strain hardening. Okay, and then all of a sudden up to the peak point, which is the ultimate strength. Okay, then the material start to lose the strength again, meaning the displacement keep going. In fact, the force is in fact reducing as well. This one here, this region here is called necking. Okay, for the further detail, it will be assigned to you later. Now, these are only axial forces, axial stresses, and axial strains. We know that there are some other forces, right? If we think about in terms of cross-section area, this one and the other and the shear force, axial force and shear force do not directly interfere each other. It is 90 degrees to each other. Axial force is 90 degrees to the cross-section. Shear force is parallel to the cross-section. Therefore, it might be some other scenario. Okay? Now, before we talk about the stress strain diagram for the shear force, we will have to talk about in more detail on how we calculate the shear strain. It's a little bit different from the for the axial strain. A rubber, the piece of material, we draw two parallel lines. Okay? This line represents the cross-section area deep into the material this way. Right? One line is one cross-section, the other line, the other cross-section. Notice that if we put the shear in it, direct shear, nothing else, try to slide it up one side and slide it down one side. Notice the movement of the line or the movement of the cross-section. One will just go up, one will just go down. No rotation, straight up, straight down. The same way, straight up, straight down on the other side as well. And that is the real phenomenon of the physical world when subject to pure shear. Once we put the shear force, pure shear force on it, notice that within that two lines, one line is moving up and one line is moving down. Let's assume this way, the one on the left go up and the one on the right go down. It could be swapped, but let's stick with this picture. Right? Once we displace it, it looks like so. Right? Notice that L doesn't change, L remains the same, about the same. Okay? What change is the level. So delta, the displacement doesn't happen parallel to L anymore. The delta is in fact 90 degrees to L. Now, if we calculate the strain the same way we think about, but this one here, it is shear strain. Okay? So then we have to talk about delta over L, right? The same idea as before. But this one is shear strain, right? Just to be clear, we change it from epsilon to gamma. Okay, you will see later why. Okay. Now notice that gamma is still displacement divided by original length, meaning length over length, the unit become 1, meaning it become dimensionless. But if we really think about it, we are still inside small displacement. Okay? If we divide like that, and delta is really small, in fact we are talking about the angle gamma here. Right? Gamma is the angle there. Now, the one I have to say this is because if gamma is an angle, dimensionless for angle, we have the name for it. It is called radian. Therefore, the shear strain is dimensionless, is an angle, and the unit is radian. Now, once we identify how we calculate gamma, maybe let's see the graph. There. Similar to last time. Just don't have the horizontal line. Okay? These are the key points in the stress strain diagram for shear. Tau is the stress, gamma is the strain. Okay, the vertical line. Okay, now the first point, if we move along from left to right, the first point we hit is in fact, we call it PL, right? Subscript PL. That is from proportional limit, because it is the stress and the strain is proportional. In another word, it is straight line function. It has a straight line relationship, linear relationship between the two. Then the second one, we realize that one is when the shear stress become the maximum of the graph. Is called the ultimate. Right? If it's stress, this ultimate shear stress. If it's a strain, ultimate shear strain. Then the last point, before at the point of breaking, it is the fracture stress, fracture shear stress, and fracture shear strain. Again, we will have a beginning section, the proportional limit section. That is the same idea as axial strain, which is the elastic zone. So that is just the tip of the iceberg yet. Okay, this is what you should read. On these two diagrams, I just present a rough idea on how they can be built and what each part of the diagram roughly means. However, there are so many details that you should read up. They are all in any mechanics of material books. You could choose your reference. Then I would like you to read further on something called Hooke's laws. It will be directly related to the axial stress strain diagram. Then about the shear modulus of elasticity. If you read the book about the shear stress strain diagram, they should be discussing shear modulus of elasticity on the same page or very close by. Find it. One more thing, the Poisson ratio. This is about how the overview of what happened to the material once it becomes longer or shorter. 4 of them that you should read. We come to the end of this lecture. So let's summarize a little bit what we have done so far. First, I represent to you why we have to study mechanics of material, right? Because it's linked directly to the task we have to work on the structure. Then we give you the overview of the mechanics of material subject. Very short, just 1 page apparently. Then we discuss in further detail the stress, the strain diagrams. Notice the plural form, because there are one for axial, there are one for shear stress. And there are some further reading has been assigned to you. And that concludes the lecture for today. Thank you.